Okay, now we're going to take a look at the ideal gas law. And this is what would work if gases were under ideal conditions. We'll talk a little bit later about what non-ideal conditions are, but this equation is very useful. And so the equation is PV equals nRT. P stands for pressure, and it can have the units of ATM, kilopascals, or torr. V is volume, and volume has to be in liters. What often happens after this lesson is that people just make all of their problems in liters and then they don't have to worry about it. So if you're doing a simple conversion problem like we've done before where it didn't matter what our units were, now instead of making that delineation, does it matter, does it count, a lot of people just put everything in liters, which is totally fine to do. N stands for moles. We use N instead of M because lowercase m means other things in chemistry later on. So N is our traditional symbol for moles. T is temperature, and I know I skipped R. T is temperature, and it must be in Kelvin. Okay, it has to be. Celsius will not work here. And then this is our gas law constant. And this constant must agree with whatever units of pressure that you use. So it has to agree with the pressure. So we need to calculate R if the pressure is in atmospheres. So we're going to use PV equals nRT. So you can always go back and calculate R if you needed to calculate it, or most people just end up memorizing it, just sort of how you learned 4.184 because we used it so much. So if we're doing ATMs, we're going to use our STP conditions. So 1 ATM, the volume at STP is 22.4 liters. N is always 1 mole for this calculation. R is what we're solving for. And our temperature is 273 Kelvin. I'm going to go ahead and solve for R, which is now 1 ATM over 22.4 liters. Or times 22.4 liters over 1 mole times 273 Kelvin. I calculate all that out, and R is equal to 0.0821, and yes, the units are sort of cumbersome, but liter ATM mole Kelvin. I know it says ATM liters, but this sort of looks like a word, and then this looks like molk, and in some ways that's easier to remember for me. So I always do my volume, then my pressure, and then molk on the bottom for moles Kelvin. If we have a different pressure, we have a different constant. So if we're using kilopascals, we also need to calculate PV equals nRT. And so my pressure in that case is not 1, now it's 101.3 kilopascals. Volume is still 22.4 liters. N is still 1 mole. R is what we're looking for, and my temperature is 273 Kelvin. I go ahead and I solve this for R, which is the 101.3 kPa times 22.4 liters divided by 1 mole and 273 Kelvin, and R is equal to 8.31 liters kPa mole Kelvin. So this is our next constant that we need to know. If R is in torr, this number here, and I'll change colors here for you, this number here would have been 760 torr. And so if I resolve it with everything being the same, this constant is, sorry about that, 62.4 liter torr mole Kelvin. So we have 3 that we need to know. The 8.31, the 62.4, and the 0.0821. These are our 3 constants that we use when we have different R values or different pressures for PV equals nRT. Now, using the actual PV equals nRT is pretty easy. And the way we identify it is all of a sudden we have moles in the problem, and we're not giving a set of changing conditions, we're giving one set of conditions. So I have 1 liters, I have 1 pressure, I have 1 moles, and I'm looking for what the volume is. So PV equals nRT. I know some of you like to rearrange your equation to solve for the variable. That is totally fine. So my pressure is 99.9 kPa. Volume is what I'm looking for. Moles in this case is 0.5. R, I need to match R to my kPa there. So I have kilopascals, and so that constant was 8.31 liters kPa moles Kelvin. And my temperature here, temperature is what I'm solving for. My volume was 20 liters. I'm going to change that there to 20.0 liters. It's actually temperature is what I want to find. Calculate the temperature. Okay. So now I'm going to go ahead and solve for temperature, and if I rearrange at this point, I end up with this 99.9 kPa times 20.0 liters, 0.5 moles, and then I have 8.31 liters kPa over moles Kelvin, and my temperature is 481 Kelvin. Fine to leave in Kelvin unless the problem asks you to convert to Celsius. Let's try one more. Calculate the moles of gas occupying a volume of 500 milliliters. Okay, red flag, that's not good. 500 milliliters, 1 liter, 1,000 milliliters is equal to 0.50 liters. Just take care of that right off the bat. With a temperature of 25.5 degrees Celsius, that's also not good. So plus 273 gives me 298.5 Kelvin and a pressure of 755. 3 different things, no change. From one to another, PV equals nRT. 755 torr is my pressure. My volume is not 500 milliliters, it's 0.50 liters. Moles is what I'm looking for. R, I need to do 62.4. Temperature, I need to do 298.5 Kelvin. I'm going to go ahead and solve for N. N is equal to 755 torr, 0.50 liters, divided by 62.4 liters torr, moles Kelvin, 298.5 Kelvin. So N is equal to 0.203 moles. And that is the ideal gas law. So we have the combined gas law and the ideal gas law.